Today we'll examine a little more in-depth chemical reactions, units 4.3 and 4.4. We do have also, on top of chemical reactions, we do have physical processes too, so maybe we should check that out before we move on. And so physical change could be something like H2O solid going to H2O liquid, or you could have it go the other direction also. So melting or freezing, and these all deal with intermolecular forces. Exceptions include bonds broken in the dissolving of ionic compounds, loss of water. What this means is these are physical processes. So let's talk about maybe you could also have a hydrate, like that little dot means there's water loosely attached. And this is also an equilibrium process. It can go back and forth. And it's certainly written as a chemical reaction, but there's no chemicals that are really changing here. No rearrangement of atoms. Yes, there's water that's now by itself. So I guess you could make an argument, but I think we're going to stick with that being a physical process. And we've mentioned this a couple times before, but it's worth mentioning again that if you break a bond, so here is water, and if you want to make this become oxygen gas and hydrogen gas, one, you're going to need two of these, and I think you're going to make two of these, but you're going to have to go, let's do it, use a different color here. You're going to have to break 4 bonds. So energy has to be absorbed in those processes. And then you're going to form, instead of making this 2, let's actually show this as 2 different, that's a plus. Let's go back to our yellow or orange, gold, or whatever. So you'd have to form those bonds. So when you form bonds, energy released. When you break bonds, energy absorbed. So I think the rest of this today will be just questions. I'm going to make this slide a little smaller so we can see it all at once. And just like many of these, I already have the answers provided. So let's just try to make some sense of this. Okay, so which of the following particle diagrams best show the formation of water vapor? Okay, so formation of water vapor, we better have H2O as a product. So how are you going to make that? You would need to use hydrogen gas and oxygen gas. And we'd also want to make sure this was balanced. So it's a 2-to-1 ratio between the two reactants. And on top of that, you have to realize that those are diatomics. A doesn't have any diatomics, so A cannot be correct. B also doesn't have any diatomics. Now C and D both have reactants that have diatomics, but let's count them. By the way, the smaller diatomics, that's going to be hydrogen gas. And I counted 6 of those. I'm just going to put 6 over here. For this is answer C. And we had 1, 2, 3 of the oxygen. Guess what? That's in the same ratio as a 2-to-1. So as it looks right now, we like that. And let's see how many waters we made. 1, 2, 3, 4, 5, 6. So a 6 to 3 to 6 is the same thing as a 2 to 1 to to 2. If we go down to D, I don't think you're going to find that that ratio. We have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And we made 1, 2, 3, 4, 5, 6. Well, that's a 6 to 6 to 6, not the same thing as a 2 to 1 to 2. So we don't like D. So if there's a chemical reaction in the question, it definitely is an advantage for you to write out a balanced chemical equation. Second one. All right, we have another chemical equation. So this one deals with silver nitrate and magnesium chloride. Oh, already mentioned here, so I didn't even have to write that down. Okay, so the silver nitrate is a 1-to-1, 1 silver for every 1 nitrate. I'm not going to count these all up, but I think they're even amounts. It's a 1-to-1 ratio between the cations and anions. The magnesium chloride, it's not that same ratio. It's 1 magnesium for every 2 chlorines. And I think that works out that way. You know what, maybe we better count these all up. I wouldn't have normally done this to answer this question, but I think this might help for explanation purposes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's 10 silvers, and I think there should be then 10 nitrates. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we have 1, 2, 3, 4, 5 magnesium ions, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 chloride ions. So what is going to be in this chemical reaction? Those would be the 2 items that would be in the chemical reaction, meaning that these should be left over. So if I go over and count 1, 2, 3, 4, 5, that's the magnesiums, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, that's the nitrates. So that doesn't even really help me answer this question yet, but that definitely gives me an idea about, was this particle diagram correct? Okay, so now we have looks like A, B, C, D answers all have 2 molar silver nitrate. So that means that this 10 and 10 with that volume in beaker X is for 2 molar. So it looks like beaker Y has the exact same volume, and it also has 5. So that would be 2 molar. Not 2 molar, sorry. It looks like it's half of 10, so it's going to be half of 2 molar, which is 1 molar. So that puts us down to answer C and D. Now, of course, we already know the answer is D, but let's try to figure out why we like 0.5 molar instead of 1 molar for the products. Well, if you dump beaker X with beaker Y, you're going to get twice the volume. And I think that shows that that volume is doubled. So if you double the volume, remember that molarity, big M, is moles per liter. So if you double the volume, it's going to have the molarity. And so that's why we got, even though over here we still had 5 mg pluses, plus 2s, we have twice the volume. So same number of moles, but times 2. So that means that the molarity will be half. That's how we got answer D. Okay, I think the rest of these are going to be more non-mathematical, more balancing equations. So what we got here? We have sulfuric acid, barium hydroxide. If you mix those two things together, you will get two different types of reactions: a neutralization and a precipitate. So neutralization is going to be with acids and bases. So sulfuric acid has H positives, and it's a strong acid, so you can fully dissociate that. Barium hydroxide is a strong base, not very soluble, but a strong base. So we could write the ions separately, and that's going to make H2O. The precipitate reaction is going to form a precipitate. What could form a precipitate? The sulfate and the barium. So what ions would make those up? Okay. Reactions with metals, in this case lithium, and water. They always give you the same types of reactions. They will make a base and hydrogen gas. So hydrogen gas, hydrogen gas, hydrogen gas, hydrogen gas. So that's not going to really help us out. Base, lithium hydroxide, lithium hydroxide, lithium hydroxide, lithium hydride. So we don't like that one. So D's off the board. So the metal is lithium. Well, they all have lithium. So that's not going to help us out. They all have water. Nope, they don't all have water. That one had H positive. So now we're down to C, B and C. So now we have to decide, do we want lithium plus with OH minus, or do we want lithium hydroxide? So this is a question about, is this a strong base or a weak base? If it's a strong base, it has to be fully dissociated. So this is a memorization style now. And you have to know that lithium hydroxide is a strong base. Another net ionic. Zinc metal. Plus hydrobromic acid. So this is like an A plus BC reaction. That's a single replacement. So that means the metal part is going to have to replace the metal component. I know it's not quite really a metal component in this case because it's an acid, but we're gonna still do the reaction in that format. So hydrobromic acid is a strong acid, so it fully dissociates. So we're only going to write the H positive, and the metal becomes an ion. And you have to know that zinc is a +2, and you have to know that H plus goes to elemental hydrogen, which is H2, diatomic. Balancing, we're done. Next, lithium oxide. So metal oxides plus water always yield the same sort of idea. They're going to make a base, and we'll see what we can do with that. Lithium oxide. It says solid, so I think it might be better in this case to leave it as lithium oxide, distilled water. And I said that's going to make a base. Well, the base would be lithium hydroxide. But remember, I had mentioned that that chemical is a strong base. So we have to write it as ions. And I think we're going to have to go like this to balance it. I think that's balanced now. Yeah. Okay, and we have a couple questions here after these nanionics. Indicate whether the pH of the resulting solution will be less, equal, or greater than 7. Since it's making that, pH will be above 7. Something about produces base. And our last one here, strontium chloride and sodium carbonate. That's AB plus CD. And those two things are going to form a precipitate. So strontium and carbonate make a precipitate. Describe what will occur if the precipitate is dried and a few drops of hydrochloric acid were added. So you could describe this with words. I'm going to use a few words, but I'm going to actually use another chemical reaction. So the hydrochloric acid, and by the way, it doesn't say that you have to write a chemical reaction. It certainly doesn't say a net ionic, but I'm going to write mine net ionically. Oops. I'm not breaking that one up because it's a precipitate. And it's going to make strontium ions. And the H plus in the CO3 minus 2, whenever you have a chance, you're almost always going to make those two components. And I think if I put a 2 there, that would be balanced. Again, it doesn't mention that you need all those, what I provided there. But you might want to provide evidence of a chemical reaction. In this case, you would observe bubbles. And I think that concludes today.